Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Okay, so today we will continue with chapter 1. Chapter 1, Introduction to Electronics Communication System, part 2. Okay, so I hope that for part 1, last week lecture, that I hope that you guys already understand. So we have covered on basic communication model, communication transmission mode, units, power measurement units, and we also have covered on the power levels, gains and losses. And finally, we have covered on the parameters involved in electromagnetic frequency spectrum. Okay, so for today, um, so if you still remember, so in last week lecture, uh, you know that modulator, the function is to convert input signal into a signal suitable for transmission channel, and that signal is an electromagnetic energy. Okay, so when we deal with signals, we will deal with what we call as noises. Okay, so basically in part 2 we will cover on noises and how to calculate for noise figure and also noise factor. Okay, so if you look at here, what is noise? So over here is stated that the noises is defined as any undesirable electrical energy that falls within the passband of the signals. Okay, any undesirable, unwanted. Okay, this is what we call as noise. So if you look at here, this figure over here, this shows the difference between a signal without noise and a signal with noise. So if you look at here, the first figure over here, this is a sinusoidal wave, okay, sine wave, and this is a signal without noise, okay. But if you have a noise in the system, you still get the sine wave, okay. So this is a sine wave, but you can see that you have, this is not a smooth line. Okay, so this is what we call as noise. Okay. So basically, noise can be divided into two. So the first one here is the correlated noise, and the second one is uncorrelated noise. So what is the difference? Correlated noise, it exists only when a signal is present. Okay, it exists when a signal is present. Compared to uncorrelated noise, this one, the noise presents all the time whether there is a signal or not. Okay, so what it means over here, for example, you have a system. Okay, so this is your input, this is your output. For correlated noise, okay, the noise exists when there's a signal, okay, when there's an input. Uncorrelated noise, the noise presents all the time, whether you have the input or you don't have the input going in the system. Okay, so that is the difference between correlated noise and also uncorrelated noise. And then for the uncorrelated noise, we can further divide it into two. Okay, we have the first one is external noise. For uncorrelated noise, we can divide it into two. The first one is external noise. The second one is internal noise. Okay, so external noise, this is the first one. The external noise is the noise that is generated outside the device. Okay, external, outside. That is the keyword. Internal is the noise that is generated inside the device or a circuit. So this external noise can be further divided into three. This one can be further divided into three, which is this one. 1, 2, and 3. Okay, so external noise can be divided into atmospheric noise, extraterrestrial noise, and the third one is the man-made noise. So what is atmospheric noise? So if you look at here, atmospheric noise is a naturally occurring electrical disturbance that originates within the Earth's atmosphere, such as lightning. Okay, so you have the Earth. This is the Earth. Okay, and outside the Earth, we have the atmosphere. So atmospheric noise is the noises originates within Earth atmosphere. Okay, such as lightning. And this atmospheric noise is also known as the static electricity. The second one, we have the extraterrestrial noise. So this extraterrestrial noise consists of electrical signal that originate outside the Earth atmosphere. So meaning that outside here. Okay, so this is your atmosphere. This is the Earth atmosphere. So extraterrestrial noise is outside the Earth atmosphere, and therefore it is also known as the deep space noise. Okay, and this extraterrestrial noise can be divided into two categories. The first one is the solar noise. The second one is the cosmic noise. Okay, so what is solar noise? So from its name, you already know that solar is noise that is generated directly from the sun. Okay, generated directly from the sun heat. While the second one, the cosmic noise or the black body noise, it is the noise that is distributed throughout the galaxies. Okay, and the third one, the third external noise is what we call as the man-made noise. So man-made noise is the noise that is produced by mankind. And these are some examples of the source of man-made noise. For example, the spark-producing mechanisms such as commutators in electrical motors, automobile ignition system, AC power generating switching equipment, and also fluorescent lights. Okay, so this is the noise that is produced by mankind. Next, let's look at the internal noise. Okay, so this is external. Next, we have the internal noise. So internal noise is noise that is generated within or inside the device or circuit itself. Okay, and this internal noise can be divided into three also. So the first one is the short noise, second is the transit time noise, and the third one is the thermal noise or random noise. So short noise, it is caused by random arrival of carriers at the output element of electronic devices. Okay, so if you still remember, I think in physics or chemistry, so you have learned on the holes and also electrons. Okay, so short noise is caused by the arrival of the holes and electrons in an output element. Okay, so the second one is the transit time noise. So it is caused by irregular random variation due to any modification to a stream of carriers as they pass from the input to the output of a device. Okay, so basically these two is similar. Okay, these two is similar, but this transit time noise is more focusing on the transit time. Okay, time. So this noise become noticeable when the time delay takes for a carrier to propagate through a device is excessive. And the third one is the thermal or random noise. So this one, the third one over here, please do not refer this one. The thermal and random noise, please refer to the next slide. Okay, so this is the explanation for the thermal and random noise. So thermal and random noise is associated with the rapid and random movement of electrons within a conductor due to thermal agitation. Okay, so if you still remember, in a material you have electrons. So when we give heat, okay, heat, panas, okay, so the movement of the electrons will increase. So this is what we call as the thermal or random noise, and it is also known as Brownian noise, Johnson noise, and also and white noise. So these are the formula for thermal noise. Okay, so N equals to KTB. So N is the noise power, K is the constant. This K is the Boltzmann constant. Okay, so please add this in your slide. Okay, so K here is the Boltzmann constant and the value is fixed. So the value for Boltzmann constants is 1.38 10 to the power of negative 23. Okay, T over here is the temperature. So temperature, when you want to use this formula, you must make sure that the temperature unit is in Kelvin, not in degrees Celsius. So if your question gives you the temperature in degrees Celsius, then you need to convert to Kelvin. So how to convert degrees Celsius to Kelvin? You just add with 273. Okay, so this is how you calculate for the temperature in Kelvin. Okay, so if for example, if you have 30 degrees Celsius, convert to Kelvin, you need to plus 273. So you will get the value in Kelvin. Okay. So this one, so this is an example to show you thermal or random noise. So for example, you have this circuit. Okay, so actually this is your circuit, this is your source, and this is your load resistor. Okay, this one over here is the internal resistor, internal resistance. Okay, so for example, stated over here, for a worst case and maximum transfer of noise power, the load resistance R, this one, is made equal to the internal resistance. So internal resistance is this. Thus, the noise power developed across the load resistor is this one. So how can we derive this? Okay, so first of all, from this statement, for maximum noise power, it stated that the load resistance is made equal to the internal resistance. So load resistance, I name it as RL equals to RI. RI is the internal resistance. Okay. So VL is equals to VI. Why VL is equals to VI? Because the current is the same. That's why VL is equals to VI. This is a series circuit, so meaning the current flows is the same. Okay, so the current flows through RI is the same as the current that is flows through RL. So VL equals to Vin. Okay, so now how to calculate for the, sorry, not Vin, Vi. So how to calculate for the VL or the Vi? Okay, so this one, to calculate for the VL, okay, you can use voltage divider. So if you still remember how to calculate VL using voltage divider, so over here you have VN. VL is equals to VN R L plus they divide by R in plus R L. But since RL is equals to R in, okay, so I name this as R because it's the same value. Okay, so you will get Vn R over 2R. And you can cancel this R, you will get Vn over 2. Okay, so VL is equals to Vn over 2, same as Vi. So now for example, let's calculate for the power. Okay, because this is N here over here, this is the noise power. So next, let's try to calculate for the power. Okay, so calculate the power at PL. The power across the load resistor. So you know that P is equals to V squared over R. This V here is VL and RL. Okay, so VL is Vn over 2. So Vn over 2 squared divided by RL. Okay, and then you calculate Vn over 2 squared. This will become 1 over RL. Okay, and your final answer will be Vn squared over 4RL. So you can see that over here, this is equals to this formula. Okay, Vn squared over 4RL is equals to KTB. Okay, and then from this, you can calculate for Vn. So Vn, you will get Vn is equals to 4RKTB square root. Okay, so this is how to derive N is equals to Vn squared over 4R. N is the noise power. Okay, so if the question asks you to calculate for the noise power, you can either use this formula or this formula. Okay, Vn over here, this is the noise voltage. Okay, so if the question doesn't ask you to derive this, then you don't need to derive. But if the question asks you to derive the noise power, then you need to show this derivation. Okay, so I hope that you understand the derivation for the noise power. Okay, so this is the uncorrelated noise. Now let's look into correlated noise. So correlated noise is a form of internal noise that is correlated to the signal, cannot be present in a circuit unless there is a signal. You must have an input signal, then only you will have the correlated noise. Okay, so correlated noise is produced by a non-linear amplification resulting in a non-linear distortion. So for correlated noise, we have two. The first one is the harmonic distortion. Okay. The second one is the intermodulation distortion. Okay, so now let's look into the harmonic distortion. So harmonic distortion occurs when unwanted harmonics of a signal are produced through non-linear amplification. Okay, so the harmonics are integer multiples of the original signals. So let me draw the harmonic distortion. So for example, you have an input signal like this. This is your V1. This is F1. Okay, so this is the input signal. Okay, so this input signal goes in a system. Then you will have the output. So for example, you have an output like this. This is V1, V2, V3 and V4. This is F1, 2F1, 2, 3F1 and 4F1. This is the output. So you can see that at the input you only have V1, but at the output now you have V1, V2, V3 and V4. So this V2, V3 and V4 is what we call as the harmonics distortion. Okay, so if you still I hope that you know that for a good system, your input must be equal to the output. So for a good system, if at the input you have a sine wave, for example, your output must have the exactly the same signal. Okay, so this is a system without any noise. Okay, but over here, supposedly when the input at the input you have V1, supposedly for a good system, at the output you only have V1. But now at the output here we have V1, V2, V3, V4, where V2, V3 and V4 is actually the amplification of V1. That's why you can see that this is F1, this is 2F1, 3F1 and 4F1. Okay, so this is what we call as the correlated noise, V2, V3 and V4. Okay, so we don't want this. The original signal is V1 only. Okay, so that is the harmonic distortion. So you can calculate for the total harmonic distortion using this formula, percent THD. So THD is the total harmonic distortion. Okay, so V higher divided by V fundamental multiply with 100%, where the V higher is V4 squared plus until Vn squared, depending on your output signal. So if your output signal have up until the 9th harmonic, then your N should be equal to 9. Okay, N harmonics. So if your harmonics is 9, so your Vn, okay, your N here is 9 up until V9 squared. Your V higher is V1. Okay, sorry. Your V fundamental is V1. Your V higher is this. Okay, so the previous figure, this is V1, V2, V3. Okay, so V fundamental is V1. V2, V3 and so on, this is the harmonics distortion. Okay, so you must include when you want to calculate for the V higher. And one more important thing is that you must make sure that the voltage is in RMS value. Okay. For intermodulation distortion, so intermodulation distortion is the generation of unwanted sum and difference. Okay, unwanted sum and different frequencies produced when two or more signals mix in a nonlinear device. So for this one, if you look at figure A, figure A this is the harmonics distortion, the one that I've already explained to you before. B is the intermodulation distortion. Okay. So if you look at intermodulation distortion over here, you must have at the input, this is input, this is the output. So at the input, you must have two signals. Okay, if you only have one signal, you will not get the intermodulation distortion. Okay, so when you have two signals at the input V1 and V2, so you can see that at the output you will have a signal like this. Okay, so instead you should have V1 and V2. Now you have another two voltages, which is the V difference and also the V sum. Okay, and look at here, the frequency for the V difference is F1 minus F2. For the V sum is F1 plus F2. So that's why the definition is unwanted summation and difference frequencies produced when there is a two or more signals. Okay, two or more signals mixed in the nonlinear device, and you will get the V difference and also the V sum. Compared to the harmonic distortion, it can exist if you have it can still exist when you only have one signal at the input. Okay, so the harmonic distortion is the multiplication of V1. So that's why the frequency here is the multiplication of F1. Okay, 2F1, 3F1 and 4F1. So this is V2, V3, V4 harmonic distortion. V different and V sum is the intermodulation distortion. Okay, so we faham ya? Other than the correlated noise and also uncorrelated noise, we have also other types of noises, such as the impulse noise and also the interference noise. So what is impulse noise? So it is a high amplitude peaks of short duration in the total noise spectrum. Okay, so this impulse noise, for example, you have a signal and suddenly you have a peak signal like this and then back again. Okay, so this is the impulse noise. It is a high amplitude peaks. High amplitude. Okay, so you can see that this is a high amplitude peaks of short duration. Okay, only short duration. So this is what we call as the impulse noise. For the interference, it is an electrical interference occurs when information signals from one source produces frequencies that fall outside their allocated bandwidth. So interference can be, examples of interference is the radio frequency spectrum. So for example, the frequency in the radio, it can be overlap. Okay, so sometimes awak dengar channel lain, but sometimes pada certain location, awak akan dengar pada radio tu akan ada dua signal overlap. So awak akan dengar dua-dua signal. So this is what we call as the interference. Okay, So it is most occurs in the radio frequency spectrum. Okay, so that one is the definition of types of noises. Okay, so now let's look into the noise parameter. Okay, so the first parameter that we will look into is the signal to noise power ratio. So signal to noise power ratio, or the S over N here, is the ratio of the signal power level to the noise power level. Okay, so this is signal to noise. So signal to noise is equals to PS divided by PN. PS is the signal power, PN is the noise power. Okay, so this is the ratio. If you divide PS divide with PN, you will get a absolute value. But if you want to have the signal to noise ratio, if you still remember, if you want to have the signal to noise ratio in the unit decibel, then you need to multiply with 10 log. Okay, so 10 log PS over PN. Okay, so you can also calculate the signal to noise ratio using voltage and also resistance. So you know that P is equals to V squared over R. So this PS here you can change into Vs squared over R in. For Pn you can change it into Vn squared divided by R out. Okay, so in the case of R in is equals to R out, this equation can be reduced to 20 logs Vs divided by Vn. Okay, so usually we will use this one lah. Usually we will use in terms of power. Okay, but sometimes we do also ask questions to calculate for the signal to noise ratio based on the voltage. Okay, so this one is signal to noise power ratio. The next parameter is the noise factor and also noise figure. Okay, so noise factor is F, noise figure is NF. Okay, so first let's look at the noise factor. So noise factor is the ratio of input signal to noise ratio to output signal to noise ratio. So this is the formula you need to remember. Okay, so noise factor is input signal to noise ratio divided by output signal to noise ratio. Okay, and you will get the noise factor. For noise figure, it is actually the noise factor stated in dB. Okay, and this parameter is used to indicate the quality of a receiver. So basically noise factor and noise figure is the same. It's just that the noise figure, this one, is the noise factor but in the unit dB. So that's why NF is equals to 10 log F. Okay, because you want it to be in the unit decibel. This one, absolute value. Okay, so this one, because you multiply with 10 log, then the unit is in decibel. Okay. Next, let's look into noise figure in ideal and non-ideal amplifier. Okay, so now let's look at noise figure in ideal amplifier. So first of all, what is the difference between ideal and non-ideal amplifier? Okay, so if you look at this figure, this is the ideal amplifier. Ideal amplifier. What it means by ideal is that this amplifier is noiseless. There is no noise. Okay, this amplifier have no noise. Okay, it only have a power gain. So if you look at here, this is the input, this is the output of the amplifier. Okay, so the signal to noise ratio at the output is Si over Ni. Now, for example, if you want to calculate the signal to noise ratio at the output, you need to multiply it with the power gain. Okay, for both Si and also Ni. So you look at here, we multiply Si and Ni with AP. So AP is the power gain. So you can cancel the AP and you will get the output signal to noise ratio is Si over Ni, which is the same as the output. So you can see that input is equals to output. Okay, so this means that this system here, the amplifier here, is noiseless. There is no noise because you get input and equals to the output. Okay, so what happens if you have a non-ideal amplifier? So this one is a non-ideal amplifier. Okay, non-ideal amplifier means that there is a internal noise inside the amplifier. Okay, so you have the AP and now inside the amplifier you have the internal noise ND. Okay, so we name it as ND, internal noise. So if you look at here, this is your input. Your input is the same as the previous example. Your signal to noise ratio at the output, at the input is Si divided by Ni. Okay, and now you want to calculate the signal to noise ratio at the output. Okay, so still you need to multiply with AP. Okay, AP Si divided with AP Ni. But since this is a non-ideal amplifier and you have the internal noise, you need to add the ND in the calculation. Okay, so now you will get the output, signal to noise ratio at the output is equals to this. Okay, and you can see that the input for a non-ideal amplifier is not equals to the output. Okay, so that is the difference between ideal amplifier and also non-ideal amplifier. Okay, so next let's look at the noise figure. When you have a cascaded amplifier, meaning more than one amplifier. Okay. So for example, if you have a question like this, okay, you have a cascaded amplifier. You have three amplifier. Amplifier 1, 2 and also 3. Okay. And this amplifier 1, you have AP1, AP2 and AP3. Okay, so this is the power gain. Okay, and this is the input, this is the output. Okay, so for example, if the question asks you to calculate for the output, okay, for the cascaded amplifier, you can use this formula. Signal to noise ratio out is equals to signal to noise ratio at the input plus the noise figure, the total noise figure. Okay, this is the total noise figure, NFT. So how to calculate the total noise figure? You need to use the Friis formula, which is this one. Okay, this is the noise factor. This is Ft. This is the noise factor. Okay, so Ft is equals to F1 plus F2 minus 1 divided by A1 plus F3 minus 1 divided by A1 multiply with A2. Okay, so since you only have 3 amplifier, then your Friis formula will stop here. But if, for example, you have 5 amplifier, so your N is equals to 5. Okay, so you should add this until F5 minus 1 divided by A1, A2, A3, A4. And you will get the noise factor. The unit for noise factor is absolute value. But if you look at here, the formula to calculate for the signal to noise ratio at the output is the noise figure, not the noise factor. This is difference. This is noise factor. This is noise figure. So to calculate for noise figure, NFT is equals to 10 log FT. Okay, so you need to multiply with 10 log. This one. So NFT is equals to 10 log FT. And this is also very important. When you are using the Friis formula, you must make sure that the noise figure must be converted to noise factor. Okay, this one. F1, F2, F3, this is noise factor. So for example, so if you look at here, this figure over here, the question, this is not a question, but example. So for the amplifier 1, it gives the value for the noise figure. NF1, NF2, NFN, NF3. This is NF3. Okay. So to use this Friis formula, you need to convert NF1, the noise figure 1, into noise factor 1. And noise figure 2 convert into noise factor 2. For noise figure 3, you need to convert it into noise factor 3. Okay? Faham eh? So now let's do example. So the first example is the question asks you to convert temperature to Kelvin. Okay, so this one is very simple. Okay, given the temperature in degrees Celsius, you need to convert it to Kelvin. Okay, so how to convert to Kelvin? It's just that you need to add with 273. Okay, so this is the formula. Temperature Kelvin is equals to degrees Celsius plus 273 degrees. 273. So for example, you want to convert 100 degrees. Okay, so 100 plus 273. So you will get 373. So the unit is Kelvin. Okay. Same for 0 degrees. So 0 degrees is equals to 273 Kelvin. Okay. And the last one is negative 10. So the temperature 3 is equals to negative 10 plus 273. So you should get 263 Kelvin. Okay. Okay, so the next example. For an electronic device operating at a temperature of 17 degrees with a bandwidth of 10 kilohertz, the question asks you to determine the thermal noise power in watts and also dBm. Okay, so remember the equation for thermal noise. So thermal noise power is equals to N K T B. Okay, so K is the Boltzmann constant, which is fixed at 1.38 10 to the power of negative 23. T here is the temperature. Okay, this is the temperature in Kelvin. But the question gives you the temperature in degrees Celsius. So you need to convert it to Kelvin first. So T is equals to 17 plus 273. So you will get 290. Correct? 17 plus 273, 290. Okay, so this is 290 Kelvin. Okay, so multiply with 290, 290 Kelvin. Multiply with bandwidth. So your bandwidth is 10 kilohertz. So 10 K. Okay, so you just multiply. You will get, you should get 4 10 to the power of negative 17. And the unit for power is watts. Okay. This is the thermal noise power in watts. The question also asks you to calculate in dBm. So how to convert to dBm? This you already learned in the previous class. So N in dBm is equals to 10 log this value for 10 to the power of 17 divided by 0.001. Okay, so you should get negative 134. You should get negative 134. This one is in dBm. But if the question asks you to calculate the thermal noise thermal noise power in decibel, dB, you just need to multiply with 10 log. Okay. The second question asks you to calculate for the RMS noise voltage for a 100 ohm load resistance. Okay, so this one you already learned, you already know the equation for RMS noise voltage. So B is Vn. Okay, this is the noise voltage. So Vn is equals to 4RkTB. So just put in the values. For R is 100. K is this one. This is KTB. So KTB is for 10 to the power of 17 square root. So you will get you will get
1.26
1.26
times 10 power of negative 7.
Okay, so the answer is 0.126 microvolt. Okay, so this is 0 0.1265 microvolt. Okay. Okay, so harap yang lain pun faham Yang this one is very simple. You just use the formula, but you must make sure that the value is correct. For example, for the temperature, use the unit Kelvin. Okay, and also please you need to remember the value for the Boltzmann constant K, which is 1.38 10 to the power of negative 23. So next is example 3. Example 3, for an amplifier with an output signal power of 10 watts and output noise power of 0.01 watt, determine the signal to noise power ratio. So this one asks you to calculate for the signal to noise ratio. Okay, so how to calculate? So if you look at here, so signal to noise ratio S over N. Okay, so S over N is equals to power, signal power divided by the noise power. Okay, so this is the signal power, 10 watt. So 10 divided by noise power. This is the noise power, 0.01. Okay. So 10 divided by 0.01, you will get equals to 1000. And the unit is absolute value. Okay, because it is a ratio. Okay, so but usually for a signal to noise ratio, we want the value to be in the unit decibel, dB. Okay, so for example, if you want to convert the signal to noise ratio in the unit decibel, you just multiply it with 10 log. So 10 log signal power divided by the noise power. So you have 10 log 10 divided by 0.01. So you will get 10 log 10 divided by 0.01. So you will get how many dB?
30.
30. Okay, so the unit is decibel. Okay, 30 unit is decibel. This one, this is also the signal to noise ratio, but in absolute value. This is the signal to noise ratio in decibel. Okay. For example 4, for an amplifier with an output signal voltage of 4 volt and output noise voltage is 0.05 volt and an input and output resistance of 50, determine the signal to noise power ratio. Okay, for example 4, the question also asks you to calculate for the signal to noise ratio. But now the question gives you the voltage, okay, the signal voltage and also the noise voltage. example 3, it gives you the question gives you the signal power and also the noise power. Okay, so make sure that you use the correct formula. So for the signal to noise ratio, for example, I want to calculate the signal to noise ratio in decibel. Okay, make sure that you use the correct formula. This is in terms of voltage. So instead of 10 log, this will become 20 log. 20 log signal voltage divided by noise voltage. Okay, so that 20 log, your signal voltage is 4, and your noise voltage is 0.005. Okay, so please calculate for this one. 58.06 decibel. Okay, so for example, if you have a question, this one, for this example 4, the signal to noise ratio at the output is 58.06. For example 3, the previous example, in example 3, okay, the signal to noise ratio that you have calculated is the TDB. So my question is, compare example 3, by comparing example 3 and example 4, which system has a higher noise? Which system is better? So my question is, which system in example 3 and example 4, which one is better than the other?
Example 3.
Example 4. Oh. Example 3.
3 or 4?
3.
Better, Why 3?
3 because the noise is a bit lower, so it's not going to disturb the system.
The noise is lower. Example 3, the noise is lower. Confirm. Which one is better? Signal to noise value higher or lower?
Higher.
Higher. So which one better? Example 3 or example 4?
Example 4.
4. Okay. So soalan jawapannya, so kalau compare example 3 and example 4, sistem dalam example 4 lebih baik. Okay, sebab signal to noise ratio dia lebih tinggi. Signal to noise ratio yang lebih tinggi memberi maksud bahawa the noise inside the system is smaller. Okay, so kalau dekat sini maybe awak agak confused sikit, but contoh, saya bagi contoh, sebab tadi ramai yang cakap example 3 better. So contoh saya bagi tadi in example 3, you have signal to noise ratio is equals to 10 log 10 divided by 0.01. So that's why you get 30 dB. Okay. This is the noise. This is the noise power, 0.01. But if you have the same system, okay, with the same signal power, 10, so 10 log 10 divide by, but now the noise power, I make it to be 0.005. Okay, so 0.01, this is 0.005. So if you calculate, this one you will get 33 decibel. Okay, so you can see that this one noise dia lebih signal power dia sama 10, but this one this noise power is smaller compared to this one, and you can see that the signal to noise ratio is higher. Okay, so you must remember that signal to noise ratio yang lebih tinggi adalah lebih bagus. Okay, so the answer is example 4 is better compared to example 3. Okay, faham eh?
Yang and input and output resistance of 50 tu apa benda?
Oh, R, resistance, tapi tak guna dekat sini. Okay, so dalam soalan ni dia bagi output resistance, okay, 50 ohm. Tapi dekat sini sebab soalan dia hanya suruh kira signal to noise power ratio. Okay, so actually kenapa dia bagi ni, macam yang ni kita directly guna this formula 20 log Vs divide by Vn. Tetapi contohnya awak tak ingat formula ni. Biasa kan awak guna 10 log ini kan. Biasa awak guna 10 log Ps over Pn. Betul? Ps over Pn. Biasa awak guna yang ni. So dekat sini kenapa dia bagi resistance? Sebab kalau contoh awak tak ingat this formula, awak boleh calculate manually lah. So Ps is equals to V squared over R. Okay, so V4, your R is 50. So akan dapat Ps. Pn pun awak boleh dapat berapa? So you can use 10 log Ps over Pn and you should get the same answer. Okay, so sebab tu dia bagi value untuk resistor 50. Tapi yang ni saya directly guna rumus 20 log Vs over Vn. Faham eh? Adakah menjawab soalan awak?
Okay, menjawab.
Okay. Okay, so next example, example 5. Okay, example 5, for a non-ideal amplifier. Okay, kat sini dia tulis, dia dah state non-ideal. Kelas awak tak ada foreigner kan? Saya cakap BM ni tadi. Okay, so tak ada, okay. So for a non-ideal amplifier, with the following parameters, determine first question, input signal to noise ratio, second, output signal to noise ratio, third, noise factor and noise figure. Okay, and the question already gives you this value. So the first one, A, calculate signal to noise ratio at the input in the unit decibel. Okay, so signal to noise ratio input. Okay, so tak kisah awak nak tulis macam mana. So macam saya tulis macam ni lah. Signal to noise ratio in. Okay, I pun boleh. Okay, in. So So signal to noise ratio in dalam unit decibel. So this is 10 log PS over PN. So PS signal power is this one. Okay. Noise power is this one. Okay. So tengok kat sini, ni dah tulis input So untuk kira signal to noise ratio at the input, kena guna yang input. Okay. So 10 log PS 2 to the power of 10 2 10 to the power of negative 10 divide by 2 10 to the power of negative 18. Dapat berapa?
80.
Ya,
80.
80. 80 dB. For question number 2, B, output signal to noise ratio. So B here, this is S over N out at the output is equals to this one the question is already state that this is a non-ideal amplifier. That's why you have the internal noise ND. Okay, so you need to use the correct formula. Okay, so for non-ideal amplifier, if you still remember, the formula for signal to noise ratio output is AP signal signal input divided by AP noise at the input plus internal noise ND. Okay, if an ideal amplifier, you don't have the internal noise. So that is the difference between ideal amplifier and non-ideal amplifier. So this one, you just put in the values. AP is this one. This is the power gain, AP. Okay, so put in the values. Signal in this one. Divide by noise power plus the internal noise. So the answer is berapa?
$25 juta.
25 juta. Okay. 25 juta. This one is absolute value because kita belum multiply with 10 log. Okay, so this is absolute value. So if you want to find the signal to noise ratio at the output in the unit decibel, so you need to multiply with 10 log. Okay, so you will get this one is equals to 74. Okay, 74 decibel. Okay. Next question C. Ask you to calculate for the noise factor and the noise figure. Okay, so for this question, you only have one amplifier, so you don't need to use the Friis formula. Okay, so for this question, you need to calculate for the noise factor first. So noise factor is F. So F is equals to signal to noise ratio at the input divided by signal to noise ratio at the output. Okay, so this is the formula for the noise factor. But please remember, if you want to use this formula, okay, the signal to noise ratio must be in absolute value, not in decibel. So this one is very important. Signal to noise ratio input and signal to noise ratio output. If you want to calculate for the noise factor, the signal to noise ratio must be in absolute value. So this one, for the signal to noise ratio ni tadi, you just divide PS over PN without multiply with 10 log. Okay, so this one, this is in decibel. So if you calculate in absolute value, so you will get the signal to noise ratio is equals to okay, so you will get this value for signal to noise ratio input. Okay, so boleh try calculate yang ni tadi.
Dapat 4.
4. Oh, 4. Okay, so the answer for this one is 4. Okay, correct. Okay, so this one, if you divide this value with 25 million, you will get equals to 4. Okay, divide with 25 million, you will get the noise factor is equals to 4. Absolute value. The second, this one, next, the question asks you to calculate for the noise figure. So noise figure is NF. Noise figure is NF. NF is equals to 10 log F. Okay. So 10 log 4 berapa?
6.02.
Okay, 6.02. 6. Okay, so this is 6 decibel. Okay. So the noise factor is 4, the noise figure is 6 dB. Okay, so any question?
Jadi FT tu apa benda pula?
Apa?
FT.
FT. FT is noise factor total. Total noise factor. Yang ada yang Friis formula tu kan? Awak tanya tu kan? FT. That one is noise factor total. Awak guna tu apabila awak ada lebih daripada satu amplifier. So this example, you only have one amplifier. Okay. So kita next kita ada example 6. So example 6 ni baru kita akan gunakan Friis formula. Sebab kat sini kita ada 3 amplifier. Okay. So now let's continue with example 6. So saya akan tunjuk macam mana awak akan guna Fish formula to solve for example 6. Okay, so for example 6, for a 3 cascaded amplifier stages, each with a noise figure of 3 dB and a power gain of 10 dB, determine the total noise factor and noise figure. Okay, so total. Okay, so this one, the question asks you to calculate for FT and also NFT. Okay, so if you have this kind of question, it is better if you can draw the system. Okay, so you have 3 amplifier, so you need to draw 3 boxes. Okay, so the first one is amplifier 1, and then you have amplifier 2, and then you have amplifier 3. Okay, and each of the amplifier has a noise figure of 3 dB and power gain of 10 dB. Okay, so power gain is A. This is AP1 is equals to 10 dB. AP2 is also 10 dB. AP3 is also 10 dB. Sebab dia kata value dia semua sama. Kalau dia bagi value yang berbeza, kena letak value yang berbeza lah dekat sini. Okay, and with a noise figure of 3 dB. So NF1 is 3 dB, NF2 3 dB, NF3 3 dB. Okay, this is the input, this is the output. The question asks you to calculate for the total noise factor and noise figure. So you must calculate for the noise factor first. Total noise factor. Okay, so since you have a 3 amplifier stages, then you need to use the Fish formula to calculate for the total noise factor. So the Fish formula is Ft is equals to F1 plus F2 minus 1 divided by A1 plus F3 minus 1 divided by A1, A2. This is the Fish formula for this system. Okay. So now you look at here, the Fish formula is F1, but the question give you NF1. Lain awak tak boleh directly guna this value. You need to convert it first from noise figure into noise factor. Okay, so first kita convert dulu. So NF1, since the value is the same, NF1, NF2, NF3, the value is the same. So you just use NF1 is equals to 10 log F. Okay, so NF noise figure is 3. So 10 log F. So you can calculate for F. So F is equals to F equals to
2.
2.
2.
Okay, so F equals to 2. Another thing that you need to remember, for the Fish formula, the power gain A1, A2, A3, the power gain here, this is A1 is the same as AP1. Okay, tak kisah awak nak guna A1 ke AP1 ke sama. So this A1, the value must be in absolute value. Tak boleh guna 10 dB masuk dekat sini. You need to convert to absolute value first. So same for this one. You need to convert A in decibel is equals to 10 log A. Okay, so A in decibel is 10. This is 10 log A. So A is equals to A equals to 10. Betul. A equals to 10. Then only you can use the freeze formula. Okay, so now just put in the values. F1 is 2 plus 2 minus 1 divide by 10 plus 2 minus 1 divide by 10 multiply with 10. So you will get the answer equals to
2.15.
2.15.
2.11.
2.11. Okay, so my answer is 2.11. Okay, yang dapat 2.15 tu saya tak sure sama ada awak salah kira ataupun memang
Salah tekan.
salah kira. Okay, so the answer is 2.11. Tapi kalau beza dia tak jauh, tapi kalau beza dia adalah disebabkan titik perpuluhan, saya bagi markah unless kalau awak salah kira dekat sini, then you will get the wrong, awak akan markah awak akan ditolak lah. Tapi kalau it is sebab the titik perpuluhan, then markah dia sama. Okay, so the answer is 2.11. This is the total noise factor. Now you can calculate for the total noise figure, NFT. So NFT is 10 log FT. So 10 log 2.11 is equals to
3.24.
3.24. And the unit is decibel. Okay, so any question for chapter 1? So this is the end of chapter 1. Kita dah habis chapter 1. So any question on chapter 1?
Doktor, kalau AP dia tu berbeza-beza, jadi kita kena kira satu-satu ke macam mana?
Ya. Yeah. So kalau AP dia berbeza, awak kena kira satu-satu lah. Ini sebab dia kata ini sebab dia kata amplifier tu semua value dia sama. So sebab tu AP1 sama dengan AP2 sama dengan AP3. Tapi kalau soalan yang dia bagi value yang berbeza, awak kena kira satu-satu lah. Dia punya AP dengan F1, F2, F3. Okay, so yang ni ada 3 amplifier . So kalau ada 4, ada 5, freeze formula awak ni akan jadi lebih panjang lah. So okay, so if you look at your ULearn, so I've already uploaded the video for last week. So if you look at week 1, I've already uploaded the video. Okay, but I think kalau awak tengok dekat YouTube, the video punya resolution lebih okay daripada awak tengok sini. Okay, so kalau awak nak video yang lebih clear, saya advise untuk awak tengok dekat YouTube. Okay, so I've already uploaded last week video, and then for this week I've already uploaded. Actually, saya baru upload this morning the notes, and also you have the tutorial. Okay, so since we have finished chapter 1, then you can try and do the tutorial. For tutorial 1, I don't think this one fully theory. So I think for this one kita takkan discuss for theory lah. Boleh refer from your notes. But the second one, this is also tutorial for chapter 1. Okay, so this one awak try dulu, and later we will discuss. If you have any question, then we will discuss. Okay, so next class awak try buat, then next class if ada problem, then awak bagi tahulah soalan nombor berapa, and then we will discuss for this one. Okay, and also don't forget to fill in the attendance. Okay, so any question for chapter 1? It will be covered in your test 1, midterm test question 1. Okay, quiz 1 will cover chapter 2. So if you don't have any question, then we can finish our class for today. Okay, so any question? Okay, so if no question, then I think we can finish our class for today, and thank you for your participation. Okay, and don't forget your attendance.
Okay, thank you, Rada.
Okay, thank you.
Ya, doktor.
Gila. Doktor, dia punya attendance tu memang by day or by week?
Okay.